Hello dear students, I welcome all of you in second lecture of Unit 2nd Sequence and Complete Matrix Space of Mathematics Paper 3rd Topology of Matrix Spaces. In yesterday's lecture, we study the definition of closed ball in matrix space. In today's lecture, we study closed sets in a matrix space. Before we study closed set of a matrix space, we revise definition of open sets of a matrix space. Open sets of matrix space. Let HD be a matrix space let capital G is subset of X G is said to be an open set if for every P belong to G, P is any point belong to G, there exists a positive real number small r greater than 0 such that open ball about P with radius r is contained in G. This is the definition of open set in X. This definition tells that if G is any subset of X, then G is open set if for every point P in G there exists a positive real number r greater than 0 such that if you draw open ball about that point which is contained in G, and this is true for every point in G, then we say that given set is open set in matrix space. This is the definition of open set of matrix space. Now we define the definition of closed sets, because definition of closed sets is related to definition of open set. Closed set let HD be a matrix space Let capital F is subset of X F is said to be a closed set if X minus F is open. This definition tells that let HD be a matrix space and F is subset of X, then this F is said to be closed set if complement of F, that is X minus F, is open set. This is the definition of closed set. That is, F is closed set if and only if its complement F complement is equal to X minus F is open in X. The set F is closed if and only if its complement is open in X. Examples. The idea is clear after solving some examples. First, let capital X is equal to R is the real line. Capital F is equal to close interval 1 to 2. Then show that F is closed set in X. This is the problem. X is set of reals and F is subset of R, which is closed interval 1 to 2. Then show that F is closed set in X. Solution. Let X is equal to R, F is equal to close interval 1 to 2, then complement of F is equal to R minus F. and is equal to minus infinity open interval minus infinity to 1 union with open interval 2 to infinity. Okay, you understand? If you have any problem, then I show you it in graph by graph. Minus infinity to plus infinity. This is x is equal to r. Set of reals. Suppose here there is 0 origin, then this side 1, 2, 3, 4, and for left side minus 1, minus 2, minus 3, minus 4, up to so on. This is up to so on. Okay, our f is this is our f 1 2. This is our f. This is our f. Our aim is to show that f is closed. That is, by definition, we have to show that complement of is open in X. This is our definition. Definition of closed set tells that to show that f is closed, that is, you have to show that complement of f is open in X or open in R. Then complement of f is the set this is the f complement. This is f complement, which is minus infinity to open into minus infinity to 1. 1 is contained in closed set. Therefore, this set complement of f contain not contain the 1, excluding 1. Also this side this is f complement. This is open to plus infinity. This is our f complement. Therefore, f complement is equal to union of minus infinity open interval minus infinity to 1 union with open interval to infinity. This is our f complement. Okay, student. To show that f is closed set, in R, we have to show that F complement is equal to R minus F is open in R. To show that, first Roman first, to show that minus infinity to 1, open interval minus infinity to 1 is open. For each p belong to minus infinity to plus 1, open interval minus infinity to plus 1, take R is equal to 1 minus p open ball about p with radius R is equal to open interval p minus R to p plus R. This is by definition of open sets. We prove this in the part of open set of a matrix space. Is equal to set X belong to R such that, this is definition of open ball, modulus of X minus P is less than R. This is equal to open interval p minus 2 p minus R is our R is 1 minus p, p minus 1 minus p, comma p plus 1 minus p. This is our interval, is equal to this open interval 2p minus 1, 2 p minus p cancel, then we get 1. Open ball about p with radius R is equal to open interval 2p minus 1 to 1, which is clearly containing minus infinity to plus 1. Since open ball about p is containing open interval minus infinity to 1, therefore open interval, therefore open interval minus infinity to plus 1 is open, This is proof. Now we have to prove that second, to show that open interval plus 2 to plus infinity is open. For every p belong to open interval 2 to infinity, take r is equal to p minus 2. Open ball about p with radius r. We take r which is in between, which is positive and between this interval. Okay, p minus, if you take p is any value greater than 2, then we get p is r is positive. Okay, is equal to open ball about p with radius r is equal to set of x belong to r such that mod of x minus r is less than p. X minus r x minus p less than r, dxp is less than r. We know that this open ball is an open interval in r, p minus r to p plus r. This is open ball in r is an open interval. Since open ball is an open interval in R, this is equal to p minus r is equal to p minus 2, p minus 2 to p plus p minus 2. This is the value of r. We put value of r in this interval, we get open interval minus 2 minus minus plus 2 to 2p minus 2. This is the open interval, and which is absolutely contained in open interval plus 2 to infinity. This open ball about p with radius r is contained in open interval plus 2 to infinity. Therefore, open interval 2 to infinity is open in R. Hence, minus infinity to plus 1, open interval minus infinity to plus 1, and open interval plus 2 to plus infinity are open set in R. This implies that minus infinity to plus 1, open interval minus infinity to plus 1, union with open interval plus 2 to infinity is also open set, because union of open set is open. This is the theorem which is proved in our section of open sets. We know that union of open set is open. Since union of open sets is open. This implies that complement of f, which is equal to minus infinity to 1 union with open interval to infinity, is open in R. Is open in R. This implies that f is closed in X. Closed in R. This is the simple solution of our problem. Now we discuss second problem. Second example. X is equal to R2 and capital F is subset of X is equal to R2, so that F is closed. Solution. Given X is equal to R2, D is equivalent metric for xy. X is equal to x1 comma x2, y is equal to y comma y2. In R2, Pxy is equal to under root x1 minus y1 square plus x2 minus y2 square. Okay. X is equal to R2, or you consider F is equal to set of order pair xy belong to R2 such that distance between xy with origin 0 0 is less equal 1. We take R is equal to 1. This is by definition of closed ball. Closed ball is less equal 1. dxy is less equal r is equal to set order pair xy belong to R2 such that under root x minus 0 bracket square plus y minus 0 bracket square less equal 1, which is equal to set of order pair xy belong to R2 such that x square plus y square is less equal 1. This is our set F. Okay. But we have to show that F is closed. That is, we have to show that F is closed. That is, we have to show that complement of F is open. To show that complement of F is open, and if F is equal to set order pair of xy belong to R2 such that x square plus y square is less equal 1, that is, F is set of all circles which has radius less than 1, then complement of F is the set of points which are outside the circle, is the F complement. This is our F. This is our origin 0, 0. This is set F. Okay. And complement of F is contain origin 0, 0, and complement of F is, this is F complement, this complement of F. Okay. Now This is point P1 comma P2. When you draw a circle about this point P1 P2, then it is containing complement of F. Therefore F is complement of F is open set. X. This is the definition of diagram of our problem and complement of F and F. Is equal to set of order pair xy belong to R2 such that x square plus y square is less equal 1. Therefore complement of F complement is equal to set of order pair xy belong to R2 such that x square plus y square is greater than 1. Because complement of F contain all point which is outside this circle, okay, greater than 1. Let P is equal to order pair P1 comma P2 belong to F complement. Distance between P and 0, P0 is equal to distance between order pair P1 comma P2 to origin 0, 0 is equal to under root P1 minus 0 square plus P2 minus 0 square, which is equal to root P1 square plus P2 square, which is greater than 1. Because P1 P2 is the point in complement of F. Let R is equal to under root P1 square plus P2 square minus 1, which is equal to dP0 minus 1. We will prove that open ball about P with radius R is contained in F complement. To show that F is complement is open, that is we have to prove that any open ball about point P with radius R is contained in F complement. Let X belong to open ball about P with radius R. This implies that distance between X and P is less than r. Consider distance between P and 0 is less equal distance between Px plus distance between x and 0. This is by since by triangular equality. Since by triangular inequality. This implies that dp0 is less equal r plus dx0. This implies that dx0 is greater than dp0 minus r, but r is equal to dp0 minus 1. This implies that dx0 is greater than dp0 minus in bracket dp0 minus 1, which is equal to 1. This implies that dx0 is greater than 1, that is x belong to a complement. Okay, we take x is a point in open ball about P with radius r, and we have to show that this x containing F complement. Therefore, this open ball is containing F complement. This implies that open ball about x about P with radius r is containing F complement. This implies that F complement is open, hence F is closed. This is the solution of our problem. Now we consider again one problem or more problem. Okay. We solve one more problem on closed set and then we stop. Okay. Third, let order pair HD be any matrix space let A is subset of X, be a finite subset of X, then A is closed. Okay, solution. XDB in a matrix space, A is subset of X, be a finite subset of X. Then we have to prove that A is closed set. This is a very simple problem. Solution: let A is equal to set. Since A is finite set, therefore A contains element x1, x2, x3 up to so on xn. This is a finite set. To show that A is closed, we will prove that complement of A complement is open. Let P belong to A complement let R is equal to minimum of distance between P and xi 1 less than I, 1 less equal I less equal n. Value of I is in between 1 and n. That is any value from 1 to n. Therefore, R is the minimum of distance between P and xi. Clearly, R is greater than 0 because X is a matrix space and we know that distance between any point is greater than 0 if these points are unequal or not equal. Choose S is less than R. We will prove that open ball about P with radius S is containing a complement. That is, any open ball about P with radius S is containing a complement for every P. Let Y belong to open ball about P with radius S. This implies that distance between Y and P is less than S, which is less than R because S is less than R. This implies that distance between Y and P is less than R. This implies that Y is not containing A. This implies that y belong to a complement. Y belong to a complement. This implies that open ball about P with radius S is containing a complement, and this implies that a complement is open. If complement of A is open, then it is prove that A is closed. This is the proof of our problem. Okay student, today I stop with this. In today's lecture, we study definition of closed sets, and a definition of closed sets is depend on definition of open set. That is, if let X is let X be any matrix space, F is subset of X, then F is closed if and only if complement of F is open in X. Okay, and we solve 3 problems on closed set. In next lecture, we study properties of closed balls and closed sets. Okay student, I stop with this. Thank you very much.